to all. Today we are going to discuss the Unit 3 data input and topology. The topic is vector data input, Digitiser, datum projection and reprojection. The course outcome of this topic: make use of JS software for developing raster and vector data model. The PO correlated with 1, 3, 5, 6, 7 and then 9, and program specific outcome 1. The outcome of this topic: make use of JS software for developing raster and vector data models. Vector data input, vector data format, shapefile. A shapefile stores non-topological geometry and attributes information for the spatial features in a data set. The geometry for a feature is stored as a shape comprising a set of vector coordinates. Because shapefile do not have the processing overhead of a topological data structure, they have advantages over other data sources, such as faster drawing speed and editability. Shapefiles handle single features that overlap or that are non-continuous. They also typically require less disk space and are easier to read and write. Shapefiles can support point, line, and area features. Area features are represented as closed loop double digitizer polygons. Attributes are held in a D-base R format file. Each attribute record as a one-to-one relationship with the associated shape records. Characteristics: raster with vector data structure. From raster, it is a usually simple, but usually it is a complex the vector data. Whereas storage requirement in the raster large for most data sets without compression. In the vector, small for most data sets. In the coordinate conversion, the raster may be slow due to data volumes and may require resampling. In vector, it is a simple. Whereas in analysis part of raster, easy for continuous data, simple for many layer combination. Whereas vector is preferred for network analysis, many other spatial operations more complex. In positional precision, floor set by cell size, whereas in raster, in vector limited only by quality of positional measurement. The accessibility of raster is easy to modify or program due to simple data structures, whereas vector is accessibility is often complex. Display and output of raster is good for images, but discrete features may show stair step edges, whereas in vector, map like with a continuous curve proof for images. The vector data input in coverage. A coverage is a georelational data model that store vector data. It contains both the spatial location and attributes descriptive data for geographic features. Coverages use a set of features classes to represent geographic features. Each features class store a set of point, lines, or polygons. Annotation text coverages can have topology which determines the relationship between features. A coverage is stored as a directory within which each features class is stored as a set of files. For example, a coverage appears in R catalog with the iconic as shown below. In this example, you can see that the stream coverage is a line coverage containing an arc line file, annotation for the line, and a tick files. There are also two versions of coverage files. Geodatabase. Geodatabase have a comprehensive information model for representing and managing geographic information. This comprehensive information model is implemented as a series of tables holding features classes, raster data sets, and attributes. In addition, advanced GIS data object add GIS behavior, rules for managing spatial integrity, and tools for working with numerous spatial relationships of the core feature raster and attributes. Whereas in CAD file, AutoCAD and MicroStation each use a proprietary file-based vector format. Both formats are capable of supporting 2D and 3D information. See the desizing of the area. Head down Digitiser. Desizing table. Use the desizing hard copy map into GIS. So transform wire intersection into coordinates of the table coordinate systems. Steps for head down Digitiser. So tape, book, control point, then map. So heads up designing. So mouse on a screen, design paper, map, aerial photo or other images. So using the mouse, we can design the area where we need to capture the location. Then we can put a point like a it is a vector data, no, so we can put the single features like a point. Then creating point, it's up designing single point features, sketch tool and snapping features. Then lines, starting and ending points with shape vertex as needed. So these are vertex points. Lines, physical attributes of tiger street. So see the shape from under two attributes, node, address, latitude, longitude, then length. So in a single table we can mention all these details. The next one is the polygon. So three or more lines joined to form a closed area, that's a polygons. So single polygons are multiple part features. So having a Iceland can be multiple polygon as one features. So the physical attributes, shape, area, perimeter and the length. Create a new feature classes created in our catalog. So through the new features we can create the catalog. So the new through the feature classes. So the R catalog we can form and add spatial reference information folder. Then we can add a new file, then finish. So feature classes created here. Now within ArcMap, the creating features layer or shapefile in ArcMap, locate an exiting data layer that is similar to the layer that you wish to create. Start editing the exiting layer, then designing the new feature. Select the new features, export the selection to a shapefile. Add the shapefile field already present and map projection is already defined. Examples in the instructor exercise. So here create the R catalog where we want to go new and feature classes and add spatial reference information, then add new files, then feature classes created. So that's are the procedure we have to follow. Then design new feature, create base map, add feature in arc map, start editing, edit toolbar, designing features, stop editing and save. So create a base map for designing. So I think you should know at the time of using the software in the system. So create an R catalog, while in the dialog box we have to create the new feature classes. Creating new feature classes based, we have to add the spatial reference information. The spatial information add a new field, maybe point line, polygon, whatever it may be. So shape future class, sorry, shape files through the future classes we can create it. So these are the steps we have to create the new feature. So see the vector feature or raster images, create base map for designing, then add new feature in the classes, then customize toolbox we have to edit and editor toolbox, toolbar to editor toolbox, then start editing, edit, start editing, then being designing, then we can design, then we can put point, line, polygon, whatever it may be, then stop editing, then edit, stop editing, then populate field in the table, then we can mention, we can edit the table, we can add the values what data we need to add in the images. So next, datum projection and reprojection. So the datum, earth, projection, map and coordinate systems. So see the earth, then ellipsoid, then scale reduction, so projection on the map plane, and we can map projection in the map. So this shape into convert into a map. So earth shape model, flat earth model are still used for plane surveying. However, distance short enough so that earth curvature is insignificant, less than 10 km. Whereas spherical earth model, the earth centered model, represent the shape of the earth with a sphere of a specified radius. Spherical earth model are often used for short range navigation and for global distance. Approximately spherical model fail to model the actual shape of the earth. The ellipsoidal Earth model are required for accurate range and bearing calculation over long distance. Ellipsoidal model define an ellipsoid with an equational radius and a popular radius. The best of these models can represent the shape of the Earth over the smooth, average sea surface to within above 100 meters. Although the Earth is an ellipsoid, its major and minor axes do not vary greatly. In fact, its shape is so close to a sphere that it is often called a spheroid rather than an ellipsoid. But sometimes the spheroid confused people, so I often called ellipsoid. So see the globe, the prime meridian, then it is an equator. So we have the particular location have the latitude and longitude towards north, south, east, and then west. So the spherical Earth surface radius 6371 kilometer. The meridian lines of the longitude passing through Greenwich, England as prime meridian are 0 degree longitude. Then parallel lines of latitude using Utica as 0 latitude, degree minute second, then decimal degree. So spherical and ellipsoidal Earth. So see the point X, Y, Z. So spherical based, the Earth centered, Earth fixed X, Y, Z, Earth centered X, Y, Z. Then geodetic latitude, longitude, then height. So semi minor axis normal to ellipsoid at point P. So point P tangent to ellipsoid at point P. Semi major axis. So geodetic height of point P. So pole, ellipsoid surface, equators, geodetic latitude at point P. Then here geodetic longitude at point P. Ellipsoid parameters. So ellipsoid parameters, the semi minor axis equal to polar radius is equal to B. WGS 84 value 6356752.3142 meters, whereas semi major axis is equal to equational radius is equal to A. WGS 84 value 6378137.0 meters. So that is a flatting. F is equal to A minus B divided by A. WGS 84 value 1 divided by 298.25 7223563. So the first eccentrical square we can calculate using this one. So see the reference ellipsoid surface map of average sea level. So the reference geodetic surface a mean sea level surface. The real surface of the earth, the ground also called the topographic surfaces. Surface compression, then model of the earth. Topographic surface, reference ellipsoid surface, reference geodetic surface. So the geodetic and ellipsoid, H is equal to capital H plus N. So head surface P, Q, N, P, geodetic, ellipsoid, this is the ocean. So small h distance along ellipsoid normal, Q to P. Capital N distance along ellipsoid normal, Q to P. Capital H distance along plumb line, P naught to P. So geodetic datum. The geodetic datum defines the size and shape of the ellipsoid earth and the origin or position and orientation or direction with respect to earth. So the direction of the minor axis of the ellipsoid is classically defined as being parallel to the mean spin axis of the earth. The position of its center either implies by adsorption or geodetic latitude and longitude, and geodetic ellipsoid is separation at one or more point datum station are in absolute term with reference to earth center of the mass. The zero of longitude, conventionally the Greenwich meridian. True geodetic datum were employed only after the late 70s when measurements show that the earth was ellipsoid in shape, the signs of the geodesy. So select ellipsoid and datum in a table, select reference ellipsoid. Then common datum used in USA, North American datum. North American datum 1983, here 27, then WGS. Then basic map projection. So a map projection is a mathematical model through the two-dimensional and distortion, and there is no best projection, conformantly scale distance direction only. So limitless way to project. So see the basic map projection. So likewise we have to azimuthal, cylindrical and conic we can provide. So azimuthal, cylindrical, conic projection. So the projection cylindrical, conic, planar. Likewise we can project it. So physical mode, distortion mode. So the assessment of the session is list the advanced Digitiser tool and list the basic map projection. So these are the reference material. Thank you.